Have you ever wondered how the ancient art of origami could intersect with the cutting-edge field of physics? Unlikely as it may seem, these two vastly different realms share an intriguing connection, one that revolves around a geometric shape known as the Amplituhedron. This shape, which emerged in the world of physics in 2013, revolutionized our understanding of particle collisions by linking them to the realm of geometry. Imagine, if you will, a shape that can simplify the intricate dance of particle interactions. Traditionally, these calculations relied on Feynman diagrams, or BCFW recursion, methods that can be as complex as they sound. But the Amplituhedron, with its unique structure, offers a more efficient way to compute these scattering amplitudes. It's as if we've swapped a tangled web for a neat, geometric blueprint. The Amplituhedron structure is based on something called Plabic graphs, a concept that may sound foreign to most. But here's where our story takes an unexpected twist. Mathematician Pavel Galashin at Cornell University discovered a link between these Plabic graphs and, you guessed it, origami patterns. This discovery helped resolve a long-standing question about the Amplituhedron's structure, known as the triangulation conjecture. This conjecture proposed that the Amplituhedron could be cleanly subdivided into simpler building blocks, much like how an origami model is constructed from a series of precise folds. So, we find ourselves at the intersection of origami and physics, where paper folds meet particle interactions and geometric shapes hold the key to understanding the universe. What if I told you that the key to understanding this lies in the folds of a piece of paper? So, what exactly is this mysterious Amplituhedron? Well, let's dive into the world of advanced physics and geometry to unravel this fascinating concept. The Amplituhedron at its core is a geometric object that emerged in the scientific landscape back in 2013. This might seem like a recent development, but in the world of science, that's quite a significant amount of time. The key to the Amplituhedron's importance lies in its transformative impact on our understanding of particle collisions. Traditionally, scientists used intricate tools known as Feynman diagrams, or BCFW recursion, to calculate particle interactions. These methods were complex and often required a hefty amount of time and computational power. But then, along came the Amplituhedron, a shape that, believe it or not, simplified these calculations. What's interesting is that this geometric object represents scattering amplitudes in particle collisions. Scattering amplitudes are essentially the probabilities of particles scattering in specific ways after a collision. So, the Amplituhedron, in a sense, is a physical embodiment of these probabilities. Now, the structure of the Amplituhedron is based on something called Plabic graphs. These graphs allow for a more efficient computation of scattering amplitudes, making the entire process of understanding particle interactions a lot more streamlined. In addition, the triangulation conjecture, a theory that confirms the Amplituhedron's subdivision into simpler building blocks, further solidifies this innovative approach. Think of it as a complex puzzle that has been broken down into smaller, more manageable pieces. The Amplituhedron is truly a revolutionary discovery. It has pushed the boundaries of our understanding, linking particle physics to the pure and elegant world of geometry. And how does origami come into this high-tech picture? You're about to find out. Believe it or not, the link between the Amplituhedron and origami patterns is not as far-fetched as it might sound. Indeed, the fascinating world of physics often finds itself intertwined with the most unexpected disciplines. And in this case, it's the art of paper folding. Let's dive a little deeper. The Amplituhedron, a geometric shape that's been instrumental in simplifying complex particle interaction calculations, is based on something called Plabic graphs. These graphs, which can be visualized through origami folds, are what form the structure of the Amplituhedron. Imagine this. You're folding a piece of paper, creating intricate patterns and shapes. Each fold you make, each crease you create, adds another layer to the final product. In a similar way, the Amplituhedron is built up from simpler building blocks, much like an origami masterpiece is built from a multitude of individual folds. But what are these building blocks? They're essentially smaller amplituhedra, fitting together in a way that forms the overall structure. This concept, known as the triangulation conjecture, has been crucial in confirming the Amplituhedron's clean subdivision into these simpler parts. Now remember those Plabic graphs we mentioned earlier? They're a way of representing these subdivisions, providing a roadmap of sorts for the Amplituhedron structure. And just like an origami pattern guides your folds to create a beautiful paper crane, Plabic graphs guide the formation of the amplituhedron. So in essence, the practice of origami has given us a tangible, understandable way to visualize these incredibly complex geometric shapes. The art of paper folding, in its elegance and simplicity, has provided a pathway to unravel the complexity of particle interactions. So, we've folded our way into a new understanding of particle interactions. But how significant is this discovery really? This isn't just about cool shapes and paper folds. This discovery has profound implications. Imagine a world where the complexities of particle interactions are reduced to the simplicity of geometric shapes and origami folds. That's the world mathematician Pavel Galashin at Cornell University has ushered us into with his groundbreaking discovery. He found a connection between the amplituhedron, a geometric shape crucial in physics calculations, and origami patterns. This discovery has helped resolve a long-standing conjecture about the amplituhedron's structure. Before the amplituhedron, physicists had to rely on Feynman diagrams or BCFW recursion to calculate complex particle interactions. Now, thanks to this geometric shape, they can simplify these calculations dramatically. The amplituhedron, since its emergence as a geometric object in 2013, has revolutionized our understanding of particle collisions by linking them to geometry. The significance of this discovery cannot be overstated. It has paved the way for a more efficient computation of scattering amplitudes, thus simplifying the process of understanding particle interactions. The triangulation conjecture, which confirms the amplituhedron's clean subdivision into simpler building blocks, further solidifies this innovative approach. In essence, Galashin's work has simplified the complex dance of particle interactions into a series of elegant, geometric forms and origami folds. This is not only a testament to the beauty of mathematics and physics, but also a shining example of how seemingly unrelated fields can intersect to solve a major riddle. This discovery opens up new doors for future research. It challenges us to think differently about the world around us and the fundamental laws that govern it. It shows us that sometimes the answers to our most complex questions can be found in the simplicity and elegance of a paper fold. So, what's the takeaway from all this? What we've unfolded today is a story of unexpected connections and groundbreaking discoveries. We've journeyed through the intricate folds of origami into the complex geometry of the amplituhedron and witnessed how these seemingly disparate realms converged, revealing profound insights into the fabric of our universe. We've seen how a brilliant mind, Pavel Galashin, made a remarkable discovery, linking the intricate patterns of origami with the complex structure of the amplituhedron. This geometric shape, crucial in physics calculations, was found to bear striking similarities to the art of paper folding. The subtleties of this connection may seem abstract, but its implications are far-reaching. This discovery resolved a long-standing conjecture about the amplituhedron's structure, simplifying the traditionally complex calculations of particle interactions. Remember, before the emergence of the amplituhedron as a geometric object in 2013, understanding particle collisions was a daunting task. It was a world dominated by Feynman diagrams and BCFW recursion. But then came the amplituhedron, a shape that revolutionized this understanding, linking particle collisions to the realm of geometry. By connecting origami patterns to the amplituhedron, we found a new way to view and compute these interactions, a method that is not only more efficient, but also more intuitive. The triangulation conjecture, confirming the amplituhedron's clean subdivision into simpler building blocks, further solidifies this innovative approach. This unfolding story serves as a testament to human creativity and the power of interdisciplinary thinking. It's a tale of how a simple art form can solve complex riddles in physics, and how the universe continues to surprise us in the most unexpected ways. Who knew that a simple piece of paper could unfold such complex mysteries of the universe?